Okay, welcome back. Um, let's continue for the lecture. So yesterday we discussed about the depth first search, also called the DFS. We also have the way to process a DFS based on the recursor. Okay, so here's the code for implement the depth first search in recursor. As we can see here, the implementation, right? It's the same as pre-order traversal, which we learned before. Okay, let's recall the pre-order traversal. Okay, so as we can see, the logic is exactly the same. Okay. Okay, let's talk about the complexity, time complexity regarding for DFS. We know the pre-order traversal, the time complexity is what? Big O of n. It means so every node will be visited exactly once. What about space complexity? For space complexity, for depth first search, we're going to define by the big O of h. What's h? H is the height of the tree, which means the space complexity is based on the how deep of the tree is, right? So it's the maximum depth of the tree, which means it is the height of the tree. What's the worst case for the space complexity? So you may store all the nodes at the deepest level in the stack at once. So the space complexity in this case will be big O of n. Okay, now we're going to talk about the tree, another type of tree called the binary tree. Okay, what's a binary tree? Binary tree, they defined each of the node has at most 2 children. They look at from left to right. Here are subtypes of the binary tree. First, it's a 4 binary tree. 4 binary trees means every node has 0 or have 2 children. Second is a complete binary tree. For complete binary tree, it means all levels are filled except the possibility the last level, filled left to right. Third is a perfect binary tree. For perfect binary tree, they defined all the interior nodes have 2 children and all the leaves are at the same level. The fourth subtype of a binary tree we call the balanced binary tree. For the balanced binary tree, the height differences between the left and the right subtrees of every node is at most 1. The last one is a degenerate, also we call the screwed tree. It means that each node has only 1 child. It can be resemble a linked list. Okay, let's see some example, the real example of this subtype. First, let's look at this tree. What do you think of this tree? We call them a 4 binary tree, right? So each of the node has 0, okay, or has 2 children. For example, B, F, G have no children. A and C have 2 children. Okay, what about this one? We can call them what? Complete binary tree. Okay, so based on the definition, all the level was filled, okay, except the last one. They filled it from the left to right. Okay, so this one don't fill the, don't have 2 children. It's only 1 child. What about this one? Yeah, this one, we can see this is a perfect binary tree. Okay, for perfect binary tree, all the interior nodes has 2 children, and all leaves are at the same level. So we can see, okay, so from all the node A, B, and C, they have 2 children. All the leaves D, E, F, G are in the same level. Okay, so this is the example of what? Balanced binary tree. For the balanced binary tree, the height difference between the left and right subtrees of every node is at the most 1. For example, right? So this, if we look at node A, they have a subtree on the left is what? Is this B, D, E. They have a height of 2. And they have the, on the right, they only have the C, the height is 1. So the difference is 1. They're not above 1, okay? So at most 1. Cannot be over, like greater than 1. So for the B, they have the subtrees from left to right is the same, right? So D and E is same level. Their height is same. All right. For C, they don't have children. They don't have a subtree. So that's it. So this tree is a balanced binary tree. Okay. So as we can see, this is a degenerate tree or screwed tree, right? So it means each node is only have 1 child. They can do what? They can resemble as a linked list. We learned about linked list before, right? So this kind of a linear linked list. Okay, this is another type of the degenerate tree, okay, or another type of the screwed tree. This is a degenerate tree. We call this one, it's a left screwed, and this one we call right screwed. Okay, let's look at the binary tree, the structure for the tree node. For binary tree, the tree node, we declare the value. Also, we have the tree node for left and right, which is different for general tree. General tree we declare as a vector of the tree node. But for the binary tree, it's very specific for the left and right. Okay, now this part, it's an initiation, or you can call it construct for once you create the binary tree node. Okay, now let's discuss about the binary tree traversal. Let's recall the pre-order traversal, which we learned for on the general tree. So for pre-order traversal, we go from one node to children. In the children, we go from left to right. So if we apply the pre-order traversal into the binary tree, we can say what? The order, we can go within what? From root node, and then we visit the left node, then go to the right node. For example, look at this binary tree. Let's go to a step of the pre-order traversal for this binary tree. So the first, we go with the root, go within A, and then we go within the left, go with B. Okay, for B, they also have the children. Okay, go with the left children D, and then go for D, there's no children, and then we go back to visit the right. Okay, so the children E doesn't have any children, and then we go back to where? To C. Okay, C will visit to left child. It's F. F is the leaves, right? There's no children. And then that's we. So for the pre-order traversal, we visit all the nodes. Okay. Okay, let's to implement this pre-order traversal into the binary tree by code. Okay, this is we just know. Okay, this is a tree node for the binary tree. We declare here. Let's recall for pre-order traversal, apply the general tree. So this is the base case. Okay, and this will be visit the current node, and then we will recursively call for each of the children. This is a general tree. If we convert general tree into the binary tree, we can see the base case is the same, and also we visit the current node. The only difference is we don't need to loop over to visit the children, because for binary tree only have the left and right. Okay, for the only have most have two children, right? Left and right. So what we do here, which is recursively to call the pre-order the node to left and doing the pre-order node to right. This is recursively call the left child and right child. Okay. Then let's look at the post-order traversal. For the post-order traversal, as we learned from the general tree, the post-order traversal, we go with the children first and then to visit the node. Okay, for children, we define as left to right. If we apply the post-order traversal into the binary tree from this principle of the post-order traversal, we know the order for the binary tree, we go from left child to right child and then visit their root node. Okay, let's look at the same example. Okay, same example. Let's process steps of the post-order traversal in this case. The first one, we go from the left, right? Left, most left child is what? It's a D. And then we visit the right node, it's E. And then we visit the root node. Okay, because D and E don't have the children. Next, we go within what? Go within the F. But there's no right child. So we go back into visit what? The parent node is C. Finally, we visit the node A. Okay, this is the steps for the post-order traversal apply into binary tree. Okay, let's look at the code. Let's recall for the post-order, apply the general tree. So this is very similar within the what? The pre-order traversal. We just put the visitor current node after the recursively call for each of the child. Okay, so this is what we learned already. Okay, we learned before for in the general tree, but we want to convert into what? Into the binary tree. Okay, what do we do here? Just instead of using the iterator for the to visit each of the children, right? Each of the children of the node, we just define the to recursively call the post-order traversal for node left child and pre-order traversal for node right child. Okay, this is for the post-order traversal, which apply for the binary tree. Okay, so now let's discuss about another type of the binary tree traversal. We call the indoor traversal. Now, in order traversal. This is just apply for the binary tree. So the order defined is from the left child, root, and right child. Okay, let's take the same example based on the definition of the order. Let's define the steps of the in-order traversal. So the first, from the most left child, it's node D, and then we go back to the D's root, B, and then we visit the right child, it's E. So on the left subtree is finished, we go back to visit the root node of the B, okay? Because this is in the B, D, E is a subtree of the A, node A. And then we go visit within the A. And next we visit the right, on the right subtree. On right subtree, what's the most left node? It is what? It is F, right? But and then we visit the root node of F. It's C. For C, there's no right child, so we complete this traversal. Okay, let's look at the code to implement the in-order traversal for binary tree. Okay, this is the code okay, so this is the code to implement the in-order traversal. As you can see, the base case is the same. Okay, so if the root is non-pointer or is empty, will be do nothing for return. Otherwise, we visit the left child, okay, to recursive call left child first, and then visit the root node, which current node, and then we visit their right child, recursively called right child. This is for the in-order traversal. Okay, so for binary tree traversal, we have been learned the pre-order traversal, post-order traversal, and in-order traversal. This traversal, they have the one common features. The common feature is they go with the depth first. So we conclude this type of traversal called the depth first traversal, also DFT. For DFT, we have to implement for this kind of traversal already in general tree. We're using the stack. Okay, so for DFT, we can implement by stack if we don't want to implement in recursively. Okay, so let's see how we can implement this traversal by the stack instead of the recursor. Okay, let's go back to the pre-order traversal again. This code is a pre-order traversal for general tree. Okay, so this is we learned before. Okay, let's quick recall this pre-order traversal. Let's look at code. This is what? This is a base case, right? This is if the node it's a non-pointer, means it's empty, will be do nothing. Otherwise, we push the root node, and then we're going to do what? To check the. Okay, so this is code. It's a pre-order. This is a pre-order. Okay, this code is implemented by stack. Okay, for the pre-order traversal for January tree. We have been learned this already. We want to convert into the pre-order traversal for binary tree. All right. Okay, so this is most of them is the same, except what? Except for push the children into the reverse to process them into left to right. Instead of we put all the children, right? Process all the children, push all the children. Instead, we just push what? Push the right and left. Okay, so we want to push them in the reverse order, so they can process from left to right. Okay, so we only have the node from right and left. In that case, we push into the node for right child and then push the node for left child. Okay, so now so in this case we can convert from the January pre-order traversal implemented by the stack for the binary tree. Okay, let's go through this code together. Okay, same example of the tree. We have the stack. Okay, so the first is root. Root is A, right? And then we push into the stack. So and then we in the while loop, we assign a node on the top, so it's A, and then we do the pump up. A is pump up, and then to display it in here. And then we push what? Push the right first, and then go within the left. So for A, what's a right? It's a right child. It's C, right? And then we push the left child. It's B. Okay, we keep going this for loop because the stack is not empty, right? So we send the node into what? Into a top, which is B, and then we do a pump up. So B is a pump up, okay? And then we displayed the B in here, and then we want to push into what? For B's child, the right child and left child into the stack. What are we going to do? The right child is E, and the left child is D. So the stack is not empty, so the while loop will be keep going. For the new node will be assigned to top. It was D, right? And then for D is pump up to print in here. For D, since D don't have any child, they are not going to, this not apply for D. And then the stack is not empty, so the loop is keep going, right? So new node will be assigned to node E, and E pump up. I'm going to display it here. For E, they don't have any child, so this not apply for E as well. And then we have the stack is still not empty. We have the C, right? Node C here. And then we assign the node is equal to node C, and then C going to pump up and display it here. For C, they don't have the right child, but they have the left child, F. So the F going to push into a stack. And then the while loop still will be continue because it's not empty, right? So the node will be assigned into the node F, and F will be pump up and displayed here. Since F note also the leaf, they don't have any children. In that case, this not applied. Now the stack is empty, so let's jump out of this while loop. So the pre-order traversal is complete. Okay. Okay, now let's look at the post-order traversal. Okay, let's recall the post-order traversal implemented by stack. I'm not sure you guys had do any exercise. Let's recall you guys do the homework after the lecture. But I provided the code for the post-order traversal. They need using the 2 stack, okay, instead of 1 stack. Okay, here's the code. You guys can review this code after. Okay, can study and review the code after. Okay, this is a post-order traversal for the general tree. We need to convert into the binary tree. Okay, again, so the only differences is to push all the children from left to right into stack. We need to change into what? Changes into specific for node left, push into the node left child, and push into the node right child. Okay, that's it. That's the only differences. Okay, let's go through this code together. Okay, same tree. We declare the stack 1 and stack 2, 2 stack. For stack 1, we push the root. Okay, the root is node A. So the stack 1 will be not empty. And the node, okay, this node will be signed into the what? Stack top. This is node A. So stack 1 pump up. So the A is going to pump up, and the stack 2 will be pushed into this node. This node pointing to the what? Pointing to A, right? So the A will be into the stack 2. Let's check for A have the left child and right child or not. If yes, going to push into the stack 1. So A have the 2 children, right? They have the left is B, node B, and the right is node C. Now let's check whether stack 1 is empty or not. So stack 1 is not empty. Okay, so the while loop keep going. Now the node will be pointing to what? Pointing to the stack 1 top, which is node C. Okay, so the node C going to pump up and push into the stack 2. Okay, now let's check about the node C has the children or not. For node C, on the left, oh yes, they have the left child, right? It's F. So they're going to push into the stack 1. Okay, the F push into stack 1. But C, there's now right child. So there's nothing to be pushed. So stack 1 is still not empty, so the while loop keep going. Now the node will point to the top of stack, which is F. So the F going to pump up and push into the stack 2. Okay. Now let's check the F have the children or not. F is a leaf node. They don't have any children, so they won't apply for this 2 length code. And let's check for stack 1. Stack 1 still not empty, and the while loop still keep going. Now the node will be pointed to the stack top of stack 1, which is what? Which is B, not B. Okay, B will be what? Pump up and push into stack 2. Okay, push into stack 2. For node B, they have children, right? They have the left children it's a D. So now the D is going to push into stack 1. And then they have the right children, it's E. They're going to push into the E, going to push into a stack 1. Okay, so step 1 is still not empty. So it will give the while loop, this while loop will keep going. So now the node will be pointing to the stack 1, the top of the stack, top of node of stack 1, which is E. E going to pump up and push into the stack 2. For E, okay, for E, they don't have any children. It's a leave node. So it's for this 2 length code does not apply for the node E. So the stack 1 is still not empty. The while loop keep going. The node going to point into the node D now, right? So the node D is going to be pump up and then push into the stack 2. Node D is still also the leaves node, so they don't have any children. And then this 2 length code are not applied for the node D. Let's check the stack 1. Now stack 1, it is what? Empty. And then this while loop is complete. Then we're going to this while loop now. Okay, for this while loop, they check the stack 2 is empty or not. Of course, stack 2 is not empty. Then what they're going to do here, they're going to print the top of stack 2 and then the stack 2 pump off after each of the elements of stack 2. So the top in stack 2 now is D, right? So D and to print also pump up, okay? So in same principle, going to display and pump up, display and pump up, keep going until stack 2 is empty. So the post order traversal will be what? D, E, B, D, E, B, F, C, A. Okay, so this is how we can using the stack to implement the post order traversal. For post order traversal, we need using 2 stack. Okay, so the first stack 1 is for the logic, to apply the logic. Okay, from the children and then from children first and then to the parent node. For stack 2, it's going to mainly to display, right? To display each of the element of the post order traversal in reverse order. Okay, so that's how the post order traversal implemented by stack. Okay, let's look at the in order traversal. You can pause here to review about this code. Now we can work together. Okay, so let's work together for in order traversal. Okay, we have the same tree and we declare the stack. We define the current node, okay, pointing to the root is A. Okay, now let's go this while loop. This while loop have 2 conditions. Okay, first is current node, check current node is empty node. Second, to check the stack is empty node. Okay, so if the current node is a current node pointer non-pointer, but it's current node it's pointer root, right? So it's not none, but stack is empty. However, we still can go into this loop, right? Okay, in this while loop, we traversal to the leftmost node. Okay, now we on the stack going to push into the node A. Then the current equal to current left. Current equal to current left. So the current now pointing to the B, right? And B going to push into the B, right? So because the current node point to B, which is not none, right? And the stack going to push into node B. Keep going, right? And then the current will be equal to the current left. So from B, the left child of B is D. So the current will be pointing to the D. So now we will push into the node D into the stack. Then the current equal to current left. D is a leaf node. They don't have any children. Now the current point to non-pointer. So this while loop is what? This while loop is complete. Now they go into this step here. Okay, so they visited the node on the top of stack. So on the top of stack is what? It's D. Okay, D going to so the current we point the current into the point into D. It's going to pump up and going to print the D here. Then we check the right subtree. So now the current pointing to D, right? D is a what? D is a leaf node. So current D, current right is nothing. It's non-pointer. So the current pointing to the non-pointer. Now let's go back in this while loop. Current point to a non-pointer, but the stack is not empty. So this while loop can continue. So currently current is point to the non-pointer. This while loop not apply. So they visit the node on the top of stack. So the current pointing to the top of stack, which is B. B going to pump up and print here. And then for the current, so far is pointing to B. B right is what? Right child is E. Now the current point into the E. Okay, now let's keep going within the while loop. Okay, so current point to the E and stack is not empty. So the while loop can keep going. And for this while loop, current point into the E is not none. So stack going to push into a node E, and current equal to current left. For E, there's no children, right? No children, no left child. So the current point into a non-pointer. Okay, because current into a non-pointer, this while loop is jumping out of this while loop and come to this portion of code. It's redefine the current. Now the pointing to the top of a stack, which is E, and E going to pump up and display it here. Current point into the E, right? E on they don't have any children. It's now right child for E, and current will be point to after this. Current will be pointing to a non-pointer. Okay. So current is pointing to non-pointer is none, but the stack is not empty. This while loop can keep going. However, this while loop now keep going because current point to the non-pointers. Okay, now let's go through this code now. Current is assigned into the top of stack. Okay, top stack is A. All right, A. So far current point into the A, and the stack going to pump up the A and display it here. Current point to the A right child. They have a right child. It's what? It's a C, right? So now the current is pointed into the C. Now the stack is empty, but the current is not empty. They point into a C. So this while loop is still continue. And this while, since the current point to C, this while loop is also continue. So the stack going to push into the what? Current, the node which the current point to, which is C. And current will be equal to current left. Current so far point to C. The left is F. Okay, the left child is F. So that's why it's keep going. So stack is going to push into the node F, right? And then the current equal to current F left child because it's non-pointer. So the current and after this current is non-pointer. Then this while loop is complete. Then we go this part. Current equal to the top of stack, which is F. F is pump up and display here. Now the current pointing to the F. F is a leave node, no children. So on the F right, okay, that's non-pointer. So the current is a point to the non-pointer. But stack is not empty, so this while loop still continue, okay? And since the current point to a non-pointer, this while loop will not apply. And for current, reassign the current into the top of stack, which is C. C is pump up and displayed here. Now we see the current is C. C don't have the right child, right? C, there's no right child for C. So current is pointing, after this, current pointing to the non-pointer. So now we can see the current is non-pointer and stack is empty. So this while loop is complete. Okay. And the in order traversal is complete. So it's going to, it's D, B, E, and then go to A, and then go to F, and go to C. Okay, this is the in order traversal implemented by the stack. Okay, there's another type of the traversal. We call the breadth first traversal. On the purest, like the pre-order, post-order, in-order, is all the depth first traversal. Now we talk about the breadth first traversal. We already learned the breadth first search in last lecture, right? So we know the breadth first, they have a character, it's for what? Based on the level. It's called the level order traversal. They visit the node level by level. Okay, so that's why we can implement this type of the traversal by the queue. Okay, so the order, as we just mentioned, but visit the node level by level from top to bottom, left to right. So we can implement by a queue. Okay, same tree. Let's process the breadth first traversal. Based on the definition, right? This order, definition of the order. First visit, we're going to from where? Going to A, and then level by level, right? From left to right. Once A complete, go to a second level. It's a B, and then C, and then we go the third level, right? D, E, and F. That's how the breadth first traversal works in the binary tree. Okay, so here's the code. We implement the breadth first traversal by the queue. Okay, let's look at code together. We have this tree, same tree. And then we declare the queue. Okay, now we push the root is A, into the queue. If the queue is not empty, right, we declare the current tree node point to the queue front, which is now, which is node A. And then we pump up. Pump up, A is a pump up, and then to print here, right? Print here. Then we will check the current, whether they have the left child and the right child. For A, they have the left child, which is a B. If they have it, going to push into the queue. And they also have the right child, is C. So they're going to push into the queue. So Since Q is not empty, this while loop can continue. Now the current node going to point into the front, right? The front node of the Q, which is B. Now we're doing a pump. The B is going to pump, and then we print here. So far, the current node pointing to B. We want to check whether B have the left child and right child. Yes, B have both have the left and right child, and then they push the left child D into the Q, and the right child E into the Q. Keep going for the while loop. Since the Q is not empty, so the current node pointing to the C. Okay, so this C is the front of the node on the Q. And then it's going to process the pump up. So the C pump up. C is a pump up and then displayed here. And we can check C, whether C have the what? Left child. Left child is F, right? So we push the node F into the Q. But C doesn't have the right child. Okay, so this code now apply for C. While loop keep going. Okay, so now the current node pointing to the front of the front node of the Q, which is D, and then doing the pump up, D pump up, and then displayed here, right? For D, this is the lib node. They have no children, no left and right child. This code now apply for the node D. So since the Q is not empty, the while loop keep going. The current node is pointing to the node E. Okay, so node E is going to be pumped out by the Q. Okay, and displayed here. For node E, also the live node, they don't have any children. So since the Q is still not empty, we keep going for this while loop. So now the current node is pointing to F, and the Q process the pump up, F can pump up and displayed here. F also the lib node, they have no children. Okay, they have no children. So these two codes now apply for F. And now the Q is empty, so the while loop is complete. So now the brute force traversal complete. Okay, so the steps of the node visit from A and B, C, D, E, F. This is level by level. This is implemented by the Q.